Hey everybody.
How you doing, Dr. Chang?
Good, how are you?
Pretty good, pretty good. Just rushed in here after work and then squeezing a little workout. And I'm in the library by myself. It's pretty creepy, actually.
Oh dang. Is the library open?
Yeah, I mean, I hope so. I'm on the third floor, but there's literally no one here.
Oh wow. Well, that's cool and creepy at the same time.
Yeah. I don't know. I'm more productive when I'm on campus. So.
Yeah, no, I feel the same way. I'm gonna eat just a little bit before class starts just because I'm coming from another class right before this.
Unacceptable, totally.
Yeah, regarding the wait list, I don't plan on adding that many students, maybe like 2 or 3 students from the wait list. And so if you're still pretty far down the wait list, I would try to look at other options for you. Yeah. Yeah, a lot of my classes are waitlisted this semester. So I mean, in the past, I've been very I said, hey, everyone come on in, but I've kind of like killed myself with the workload, and so I was gonna wait and see that maybe some of my other classes aren't as waitlisted as much, and so I can add more here, but I want to be fair across all my classes. Yeah. Yeah, so if you're still fifth, I mean, you can check and see. Maybe we'll have a change of heart after today, seeing all the MATLAB. But if you're still that far down tomorrow, then I would probably find another option. All right, it's 7 o'clock, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Good, great. Okay, great to hear. Good to hear. Yeah, so it's still the first week, so everyone's still happy. So that's that's a good thing. I think people get stressed later on, but it's good that everyone's still doing well right now. All right, and so today the plan is to do just a review of MATLAB. Okay, so I've actually changed this from last year. So in the past, I've kind of had a hybrid of kind of both reviewing some mathematical concepts, but also MATLAB. But I think kind of the feedback that I got from past years is that people would prefer kind of more review of MATLAB, and then the math stuff with theory. I think we'll kind of review those kind of as they come up. When we start to do derivations and things like that. So today will just be all MATLAB. And so if you want to follow along today, you can definitely do that. So I designed these lecture slides to be quite interactive. Okay. And so if you want to open up MATLAB so you can follow along, that would be great. But if not, you can always just kind of just sit back and kind of watch me do MATLAB. Okay. So I did renew my license, and so I told you guys that I had a working MATLAB license, and so it is working. I tested it out before this, and so we're good to go. Okay, and so before we begin, are there any questions I can answer? Okay, all right. So let's go ahead and just jump right into it. Okay, and so let me just give a little brief introduction of what MATLAB is and why we're using it. Okay, just kind of very briefly. And so first let me talk about just the idea of computational engineering, which is what finite elements kind of fits into, right? And so when people mention computational engineering, that basically refers to any work that engineers do that uses computers or computer software to augment their work. Okay, and I call it that on purpose, because I don't want people to think that computers are replacing engineering work, or that they can do the work of engineers. Computers are really just there to augment the work that engineers do. Okay, and the main reason for this and the main benefit of using computers is that computers can perform calculations that are way faster than humans. Okay, given that they're set up properly, right? And so that's the main thing, right? And so the way that engineers typically use computers to do their work is that they have to formulate their engineering problem or put it in a way that computers can understand, right? And so at the most basic level, the way that we do this is by coding, right, or programming. And even the softwares that you've probably used. So you've probably, I know a lot of people are coming from 540, and so you're probably familiar with ANSYS, and so you're probably also familiar with softwares like SolidWorks, right? And so even though those have graphical user interfaces, at its core, at its base, they were coded and programmed by engineers. Okay? And so in this class, we're going to be focusing a lot on the coding aspect, right? And so there's a lot of different languages that we can use for coding. And so there's MATLAB, obviously, which we're going to use. There's Python, which is very much kind of dominating more and more of the space every day. There's C++ and Fortran for kind of the more intense people out there. And there's a new language out there called Julia, which has a lot of great benefits. And so if you've heard of Julia, maybe in 5-10 years, that's probably what's going to take over, but because it has a lot of really great benefits, but right now it's still kind of finding its way. Okay. And the application that we're going to be using it for in particular is it's going to basically able to simulate reality by solving differential equations. Okay. All right. So what is MATLAB? And so MATLAB is a specific program, or some people think of it as a programming language that is specifically designed for performing mathematical calculations, right? And so it was designed kind of from the ground up for ease of use compared to some of the other programming languages with relatively simple conventions and many built-in functions. It's widely used, mostly in the educational space, but it's also used a lot in research, and it also has some engineering applications as well. Compared to some of the other languages out there, it is slower, and so it's not going to give you the same kind of performance as an equivalent code in Python or C++ or Fortran. So you often don't see many big codes written in MATLAB, and so your programs like ANSYS or SolidWorks, those aren't written in MATLAB. But it's great for quick prototyping, and so because of its simplicity, because of its ease of use, it's really easy to kind of jump into MATLAB and just code something up really quickly to see if it works, without having to worry too much about that. Okay. And if you want to get technical about it, and if you if you ask, if you have a friend that's in computer science and you tell them MATLAB is what you're learning to program in, they'll be like, oh, well, actually MATLAB is technically a scripting language, which is not the same as like a coding language, but for all intents and purposes, for what we're using it for, it's a programming language. It's something that we can code in. Okay. All right. And so again, why we're using MATLAB. So, a big reason for that is it's commonly taught. And so I think a lot of people here are coming in with at least some degree of MATLAB experience, because it's what's taught in the classroom. Another reason is, MATLAB has a lot of built-in functions, which are really useful, and that basically allows us to focus on the theory and the fundamentals without kind of getting bogged down with the programming, right? The error messaging is relatively useful, and so MATLAB does a pretty good job of telling you what's wrong, and it has a really nice plotting capabilities and very strong online community as well. And so a lot of times, if you have issues with MATLAB, there's a bunch of people online that can help you out, right? And relatively speaking, is cheap compared to other softwares out there. Okay. All right, and so let's so now now that we've talked about why we're using MATLAB, let's get into the details of how we actually use MATLAB, right? And so the first step to using MATLAB and to using any programming language in general really is to define variables, right? And so variables, variables are basically labeled entries in a computer program used to store information, right? And so the thing with whenever you're coding or whenever you're programming, you're going to be generating a lot of data and a lot of information, through the program and through your calculations, right? Variables are basically your, you can almost think of them as like little, little scraps of paper, right? And so your variables are going to be there to store that information for you, which you can use and manipulate later, okay? And so the key here is really storage, right? And so whenever you need to kind of store something or kind of remember something in your, in your program, you're going to use a variable to store it, right? And and we use variables a lot when we're programming. And there's lots of different forms of variables out there, and so the form that a variable takes, depends on the nature of the data that you're trying to store, right? And so kind of broadly, the three different types of variables that we can use in MATLAB are scalars, right? And so when I say a scalar, that basically means the variable just stores a single value or a single number. Okay. We have a vector, where a vector stores a series of values or a collection of values, and this is organized as a list, right? Or a matrix, right? And so a matrix also stores a collection of values, but the way it organizes it is different. And so instead of organizing as a single one-dimensional list, it instead stores it as like a two-dimensional construct. Okay. All right, and so that's that's what variables are and what we use them for. And so now let's get into the syntax of how we actually define them, right? And so when we define a variable, we need to give two things, right? And so the first thing we need to give is a name for the variable, right? And so that's how we're going to refer to it later. And we also need to give a value to the variable as well. Okay. Right. And then the way that you connect these two is the equal sign operator. Okay. And so as an example, very, very simple example, let's say that we want to create a variable and store the value of 6 inside that variable, right? And so the way that we code this up in MATLAB is say that, we give the variable name. And so in this case, the name of the variable is scalar example. Okay. And then we're going to assign a value to that variable as well. Okay. And so in this case, we are assigning a value of 6, right? And so after we execute this line of code, right, and so we go kind of later on in the code, this variable is going to be another way that we can call upon the value of 6, right? And so that's kind of the basics of defining a variable, right? And so you have to give it a name, you have to give it a value, and you have to give it an equal sign, right? Okay. The equal sign is very important because the equal sign is used a lot in MATLAB and in programming in general. And it has a very special purpose of assignment, okay? And so whenever you want to assign a value to something, assign a value to a variable, you have to use an equal sign, right? And so another way that you can think of the statement here is we're going to assign a value of 6 to this variable right here, scalar example. Okay? And the way we do that is through an equal sign. Okay. All right. Any questions on this so far? Okay. Okay, and so now that we've defined that variable scalar example, now we can now we've stored that number 6. Okay, and so most of the time, when we define a variable, we do so because we want to use it later on in the code, right? And so by storing that value, it basically allows us to use it later on, right? And so we can define another variable that's a function of that previous one, right? And so we define a new variable called scalar operation. Okay. What we say is that its value is going to be equal to 3 times scalar example plus scalar example, right? And so let's go back to our previous slide and kind of remember, what the value for scalar example is. Okay, and so from here we can see that the value of scalar example is 6, right? And so let's go ahead and plug that into this equation, right? And so we have 3 times 6 plus 6, okay? And so if we perform this arithmetic, we do 3 times 6 plus 6, what we get is 24, right? And so 24 is going to be the value of this of the scalar operation right here. Okay. Right. And so this is a very common way to use variables, right? And so the reason we store values in variables is because we want to use them later on in the code. Okay. All right. And so that's scalar variables, and that's scalar operations. And so now let's talk about how we define vectors, right? And so vectors we define very similarly, but remember, vectors are a collection of variables, organized as a list, right? And so the way that we define it is, we again use a variable name, we again use an equal sign, right? But instead of a single scalar number, we're instead assigning a list of numbers instead. Okay, and so in this case we have a 3-item vector, and so it's 7, 1, 4. Right? And we use these commas to to separate out those variables, okay, or separate out the values. I'm sorry. Okay. Right, and then just like we did with scalars, we can perform operations on the vectors, right? And so if we do vector operations equal to vector example plus this, okay, then our result is also going to be a vector. And then what we do is we do just very simple vector addition, and so we add up the entries that are in the same in the same spot. And so in this case, the 7 from the first one is in the same slot as 4 on the second one. And so we do 7 plus 4, which is 11. Okay. Next, we have 1 in the second slot on the first one, and 1 in the second slot of the second one. And so that's going to be 2. Okay. And then finally, we have 4 in the slot of the first vector, and we're adding a 2, 7 there. Okay. And so that's going to be 11 right there, right? And so the result of this operation is a new variable, right? And so remember, we're assigning this variable value, okay? So that's going to be stored in here. And so vector operation is going to be equal to the vector 11, 2, 11. Okay. All right. Any questions on this? Okay. All right, and so that's kind of the basics of defining scalars and vectors, right? But there's other ways that we can define vectors as well, right? And so there's some specialized functions in Matlab that kind of lets you do this, right? And so the first function that I want to go over is one called linspace. Okay, so this is a pretty useful function, and what this does, it creates a vector where each of the entries is equally spaced apart. Okay. And so you can see here that we have this sample line of code here to create this this vector called linspace example, right? And so to do that, we're calling the function linspace with 3 different arguments here, right? And so let's look at this kind of description here to see what each of those arguments mean, okay? And so the 0 here, which is the first argument, that defines what the first entry in the vector is going to be, okay? Next, we have this 10. And so the 10, what that describes is what the last entry of the vector is going to be, okay? And this last number in the argument 5, this defines how many entries that we want in the vector overall, okay? And so in this case, we want 5 entries in the vector, okay? And so we can count them here, 1, 2, 3, 4, 5, right? And so what this is telling Matlab is says, hey, give me a vector where the first entry is 0, the last entry is 10, and there are 5 entries overall in this vector, right? And they all have to be equally spaced from each other. And so you can see from the result here that this is 0, 2.5, 5, 7.5, and 10, right? And so this vector here, which is created automatically within Matlab, satisfies all our criteria for the, from the function, right? So it starts at 0, ends at 10, and everything else is kind of equally spaced in between there, okay? Another common function that we're going to use a lot in this class is called the zeros function. And so the zeros function will create a vector or matrix of a specified size where every entry is 0, okay? And so this is really nice because, we're going to use this actually quite a lot in this class to kind of define our vectors, right? And so the example below here creates a vector that has 100 entries, okay? And every single entry is going to be 0, right? And so if we kind of draw out what this vector looks like, it looks like 0, comma 0, comma 0, comma 0, comma 0, comma dot, 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 right? 0, comma 0, comma 0. Where this right here, this is the 100th entry. Okay, because this vector is 100 entries long. Okay. All right. And so, just be aware of these two special functions because, maybe in linspace I won't use all too much, but we are going to use zeros quite a bit because creating an empty matrix or an empty vector is something that's really useful for finite elements. Okay. Any questions on this?
Yeah, Professor, how do you manipulate the size of the rows and columns of the zeros vector? Do you do it with the second value?
Yeah. No, great question. And so to manipulate the size of this vector, we define the dimensions here. And so these two numbers here define how many rows and how many columns you want in your zeros vector. Yep.
Okay.
And so actually, I kind of drew this sideways, and so this should actually be transposed. Right?
Okay.
Yeah, don't you have 100 columns there?
Yeah, so it's top down.
Yeah. So I kind of did this reverse, and so just because I kind of drew it horizontally, so this is 100 columns. In reality, it should be a vertical vector right here. So it should be 0, 0, 0, something like that, because we have 100 rows here and only one column. Right. Okay. Yeah. Thanks for catching that. Okay. All right. And so now let's talk about manipulating variables. And so once a variable is defined, it's not like it's stuck with that value. So you can actually manipulate the value of that variable, however you see fit. Right? And so this means that we can take the same variable name but change its value, so that variable name represents something else. Okay. And so the way we do this is we use the same equal sign operator. Okay. And so if you remember from earlier on in the lecture today, we used this variable here, scalar example, and we assigned a value of 6 to it. Okay, but now we're going to change its value, and so now it's going to have a value of 9. Okay, and so now this changes the value of this one from 6 to 9, and this is totally fine. And so and in fact we actually want to do this a lot because maybe we need the value of 6 for one part of the code. But for a different part of the code, we need a value of 9 there. And to change this value here is totally fine. Okay. And so here's an example here of using other variables to change those values. Okay. All right. And so you can see here that I've created a variable called new variable, and I've assigned it an initial value of 7. And I defined another variable with the name whodis, and I assigned it a value of 2. Okay. And so what I want to do from here is that I want to manipulate, or I want to change the value of new variable so that it depends on whodis, right? And so we have new variable is equal to whodis plus 5/2 times whodis, right? And so if we plug in whodis here, and so we have 2 here, 2 here, right? And so we have new variable is equal to 2 plus 5/2 times 2, okay, which is 5. And so in this case, we actually end up with the same value for this variable, which is 7. But if instead I change this 5/2 here to be something like 7, right? And so we have new variable is equal to 2 plus 7/2 times 2, and that result will be 9. Okay, and this initial value of 7 here will be forgotten, and now new variable will have a value of 9. Okay, all right. Another technique that we can use when you're coding is to update the value of a variable, right? And so this is actually really valuable, and I think it's one thing that I think confuses a lot of people, is that you can use you could update the value of a variable using its old value. Okay, and so let's take an example using the whodis variable, right? And so let's say that we want to update the value of whodis to be 11 instead of 2, right? And so one way that we can do this is we can say that whodis is equal to whodis plus 9, right? And so the way to kind of read this as a sentence is to say that the new value of whodis, and the equal sign means is, this means the old value of whodis plus 9, right? And so if you kind of read this as a full sentence, you can say that the new value of whodis is the old value of whodis plus 9, right? So the old value of whodis is 2, right? And so the new value of whodis is 2 plus 9, which is 11. Okay. And so now whodis is going to have a value of 11, and it's going to forget its previous value of 2. Okay. So this update notation is actually going to be really critical, because we're going to have situations where we're going to be modifying entries in very large matrices, and we don't want to forget what we had before. We just want to add to it, right? And so this update notation here is going to be really, really useful for us, right? And so you're going to see this kind of syntax come up again. And so whenever you see the name of the variable on both sides of the equal sign, just know that whatever you see on the right hand side is going to be the old value of the variable, and what's going to be on the left hand side is the new value of the variable. Okay. All right. Any questions on this?
Yeah, Professor, I'm just a bit confused by this. I thought with MATLAB, every new variable had to have like a new name. So how does this work when you run the code? Does the earlier part of the code use the previous value of that, and then it gets updated as it runs along?
Yep, exactly. And so MATLAB code is always read kind of from top to bottom. And so let me go ahead and clear this. And so let's kind of just write a quick pseudocode here, right? So we can say that whodis, let's say we give it an initial value of 2, right? And then we have another line here where we have a variable, I'll just call it x for simplicity, right? Okay, and so we can say that x is equal to whodis plus 3, right? And so at this point in the code, whodis has a value of 2, right? And so we can say that x is equal to 2 plus 3, and so it's going to have a value of 5 right here. Okay, but then later on in the code, if we have an update to the variable, right? So we say that whodis is equal to whodis plus 9. Okay, then we're updating the value of whodis, but this doesn't occur until much later on in the code. And so if we make a new variable here called y, which is equal to whodis plus 10, okay, this since this line occurs after whodis has been updated, then this is going to contain the new value of that variable, right? And so the new value of this variable is 11, and so this is going to be 11 plus 10, which is equal to 21. Yeah, so everything is read sequentially. And so if you have a line of code that occurs before the variable was updated, then it's going to have the old value of that variable. Okay. All right, any other questions on this? Okay. All right, and so let's talk a bit about how we use variables. So variables can be used in a lot of different ways within a program, right? And so the first use of a variable is to kind of just act as permanent storage. And so, let's say that we have a number that we always want to refer to later on in the code. And so we can just store that as a variable and then just kind of use it, later on. Okay. And so one example of this is, let's say that we have the say we want to input the radius of like a circle or something, right? And so we can define a variable called radius, and that equals 4, right? And then later on in the code, we can have a line of code that says area is equal to pi times radius, okay? Where this radius is referred to up here, okay? And so variables like this, in MATLAB, they don't really make the distinction, but in other programming languages, you can call this what's called a const, okay? A constant value, which means that the value of this variable is never going to change throughout the program, right? And so it's simply used as storage, or in other words, it's simply used as a way to organize your code, okay? And so we're going to be using a lot of these as well, because when we set up finite element problems in the code, there's going to be a lot of variables that we don't, we kind of define at the beginning and we kind of just use them throughout, okay? And so this form of using variables like this, I'd like to call these as like setting parameters, okay? Because a lot of times when you're doing a physical problem, or you're doing a computation, there's certain parameters of the problem that don't change, throughout the computation, right? And so some examples of this would be like geometric properties, right? And so if you're running a finite element simulation on a certain geometry, you want to store certain features of that geometry as parameters so that you can refer to them later on in the code, right? So these parameters don't change as you run the code, but they're important to keep track of. And so we store them as a variable, okay? All right. Another important use for variables is to store them as values for calculations, okay? And so these are often used as like temporary storage, okay? And so the difference between these is that these are not real parameters, and so these are kind of almost like temporary placeholders. So a lot of times when we perform calculations, we compute something and we want to just kind of save it temporarily, just so that we can use it in the next stage of the computation. But then we kind of just delete the one above that, okay? And so the difference is that these variables are being constantly changed and updated according to the algorithm, okay? All right, and so I'd say kind of broadly, those are kind of the two main ways that we'll use variables in this class, okay? Kind of on a superficial level, kind of more simply, the way I'm going to organize the codes in this class is that the variables that are meant to be parameters, I'll put these usually at the very top of the code, okay? Okay, and so if you see a variable defined near the top of the code, then those are most likely going to be parameters that we're not going to change the values later on. But there's also going to be variables that are defined kind of throughout the body of the code, and those kind of fall into this category where they kind of just act as temporary storage just for the sake of calculations. Okay, and so I'm going to be very explicit about that. And so organizing your code is something that helps a lot when you're programming, just to kind of keep track of everything. And for a lot of the assignments I'm going to give you kind of a skeleton code where I kind of do a lot of that organization for you, where I said, here's the very top section, here's where we're going to define our parameters, and then later on these are variables that we're going to use for calculations. And so I'll be kind of very clear about that, just to kind of help you out. Okay, all right. And a good kind of rule of thumb, or not rule of thumb, a good word of advice when you're writing kind of any kind of program, is when you're giving names for your variables, right? The names you give your variables are kind of up to you. And so you can kind of use whatever names that you want, but I really, really encourage you to use descriptive and distinct names for your variables, okay? And so I think what a lot of people do when they first start to program is just that, they use single letter names. And so they use variable names like X, or they use names like Y, right? In their code. And not only does this make it a lot easier to make typos later on, but it also makes it really easy to really difficult to debug too, because you might define X, X is equal to 5 on like line 3 or something, right? And then later on in your code, you might be on line 4000, and you have some equation that involves X, right? And then, when you're looking at line 4000, you'd be like, what the hell what value was X? What is X? I've never heard of that before, because it was defined, way up here. if instead you use kind of a more descriptive name for X, and so instead of X, maybe X is meant to represent like the, I don't know, the length of the bar, right? And so you use length instead, right? Okay. That's a much better name. And so when you're on line 4000 and you see this, really long equation, and you see length, and it's like, oh yeah, length, I know what that means automatically, instead of X, which is, you may not know what that means, right? And I've also seen, and I'm the most guilty of this. In frustration, I give my variable names kind of very inappropriate names, and so I've given names, like, why the fuck won't this work? And that's also not useful. Not only does that take you a long time to type, it kind of runs you into the same problem where you have that variable name somewhere down here in the code, and you're like, I don't know what that means, and then you kind of hate yourself and even more, and you kind of it becomes a spiral of lots of cursing at your computer, which is usually not healthy for anybody. All right, any questions on this so far? All right. Okay, and so those that's kind of the basics of defining variables. So now let's talk about defining matrices. Okay. So matrices, I have a section for matrices because they're very important data structures for computational engineering. Okay. Because really they form the backbone of linear algebra, right? And so anytime you have a system of equations, a lot of times you want to put them in a matrix form so that you can perform the calculations. Okay. And this is really useful because what we'll learn later on is that computers are really, really good at performing linear algebra, versus differential equations. And so, a lot of what we're going to do is we're going to take these complicated physical problems and transform them into an algebraic system that the computer can solve. Okay, and so we're going to be using matrices quite a bit. Okay? And so there's a couple different ways that you can define a matrix. And so the first way is kind of what I call like the manual way of defining a matrix, right? And so this is probably a way that you've seen before, where we define a matrix kind of, all in one line like this, where we say that, we kind of define it row by row, where you define, each row separated by colons or commas, excuse me, and then you use a semicolon to go to the next line, right? And so in this example here, we have a 3 by 3 matrix where the first row is 1, 1, 1. The second row is 9, 9, 9, and the last row is 4, 6, 8. Okay, and you can see that we've separated each row entry by commas, and we've gone to the next row using semicolons, and then we create a matrix that looks like this basically. Okay, all right, so that's fairly straightforward. But I will say that we're not going to use this form of matrix definitions a lot. Okay, we're going to use this form a lot more often in this class, right? And so even though the previous form is really compact, it only really works if you know all the matrix values kind of beforehand, right? And so when you're defining the matrix, if you know what every entry should be, when you're defining that matrix, that works great, okay? The thing with finite elements is that, a lot of times we don't know what our matrix is going to look like, or we don't know what the values of the matrix are going to be until we actually start doing some calculations, okay? And so another way that we can define a matrix is we can use that zeros command that we talked about before, right? And so if we have let's say that we want to create a 3 by 3 matrix, and we're going to create it as a zeros matrix first, okay? And so we're going to say that zeros matrix example is equal to zeros 3 by 3. And so this creates a 3 by 3 matrix, which is all zeros, okay? Okay. And then from here, what we can do is we can assign the individual entries, okay? And so, let's say that the entry in the first row in the first column is going to be 1, okay? And so after doing that line of code, then this entry here will be 1, okay? Next, we're going to do the first row and the second column, and so that's going to be 1 right there. Then we have first row and third column, and so that's going to be 1 right there, okay? And so we can do this for every single entry in the matrix, right? And notice how we're doing this, right? And so to assign a specific entry in the matrix, we're using the variable name, and so in this case, which is zeros matrix example, and we're using these parentheses to refer to a specific entry in the row and column of that matrix. Okay. And you're probably looking at this and you're saying, this line, this chunk of code right here, this chunk of code does exactly the same as this one line of code, right? And so why the hell would we ever want to use this form right here if it's going to take us that much more work and that much more typing, right? And the reason for that is, like I mentioned before, because of the way finite elements works, we don't know, what all of our entries and what all the values of our matrix are going to be kind of beforehand. And so the way that we actually construct our matrices is to kind of first construct kind of an empty matrix, right? And then update the entries, as we chug along in our calculation, right? And so we're going to create an empty matrix, and then as we do our calculations, then we're going to update the entries of the matrix in order to reflect the correct values. Okay. Another reason why we'd want to do this is that we're often going to work with matrices where the vast majority of the entries are actually going to be 0. Okay. So this example here is not really indicative of what finite elements looks like. And so oftentimes in finite elements, we're going to be working with ginormous matrices. I'm talking like 10,000 by 10,000. Okay. Okay. And so, way too big a matrix to fit here. And I will tell you that, probably 98% of those entries are going to be 0. Okay. It's only going to be a select few in this 10,000 by 10,000 matrix that are going to have non-zero values. Okay. And so in this situation where you have a huge matrix and only a few of them are non-zeros, it actually makes a lot more sense to use this form right here, where you create an empty matrix first and you only assign the values that are non-zero. Okay. Versus, this example right here, where can you imagine writing 10,000 entries, 10,000 times 10,000 entries here, just like that, where the vast majority of them are 0. You'd probably go crazy just trying to type all of them, and you probably wouldn't count it up right anyway. Okay. And so those are kind of the two reasons why we use this form right here. And so I know kind of initially it's going to be a pain to use this because it feels like you're wasting a lot of time and you're typing a lot of stuff, but this is kind of the convention that we're going to use for most of this class. Okay. Yeah, and for loops, and we'll get to for loops in a second, but and for loops are basically the way that we assign these entries in the matrix. Yeah. And so one common thing that you'll see is that we'll create a really big empty matrix, and we're going to use for loops to assign the values in the matrix that are not 0. Yep. All right. Any questions on this?
I guess I'll find this out when we actually do it, but so do we know the size of our matrix that we're going to end up with at the end of the calculation?
Yes. Yeah. You'll know the size of the matrix at the very least, and so that's why this function is really useful to us. And so we'll know how big our matrix is. It's just a matter of filling in the correct entries in the matrix. Yeah.
Okay, and then I guess we'll just see from our result which entries need to be non-zero.
Exactly. Yeah.
Okay.
Yeah.
Alrighty.
Yeah.
Thanks.
Yeah. So it's definitely a different mindset, because a lot of the problems, they quickly become too big to solve by hand. And so instead of kind of manually assigning each entry that should be non-zero, you kind of write an algorithm that tells the computer these entries are going to be 0. The non-zero entries follow this kind of pattern, and then you kind of trust the computer to kind of fill in those entries exactly as you specify. Yeah. Well, I have a couple example problems at the end that kind of give some good examples of that. Yeah. All right. Right. Okay. And so, speak of the devil. So, like I mentioned before, that one thing that we're going to do a lot in this class is updating existing entries in a matrix, right? And so remember before, I gave you the syntax for updating the value of a variable. We can use that exact same syntax to update the value of a specific entry in the matrix, right? And so, in this example here, we can say that, let's say that we want to update the value of the 1-1 entry from the previous example, right? And so we can say that the 1-1 entry of zeros matrix, the new value of this is going to be equal to the old value of what was in that spot plus 47. Okay. And so I believe the in the previous example, or the previous page, the 1 entry had a value of 1. And so at the conclusion of this line of code, this entry here is now going to be 48. Okay. And so after executing this line, our matrix is now going to be 48, 1, 1. I believe the second line was 9999 or 999, and then 2, 4, 6. Okay. And so you can see here that we've updated this entry in the matrix using this line of code right here, right? And so we took the old value that was there before. And so before we did this calculation, the old value there was 1. And so we did 1 plus 47, which is 48. And then we store that 48 into that entry in the matrix right there. Okay. All right. And so this is something we're going to do a lot, because we're going to be building these big matrices, and we're going to be updating its values according to our finite element calculations. Okay. All right, any questions on this? Okay. All right. And so now that we've kind of have the basics of variables, now let's talk about how we actually solve a linear system of equations. Okay. And so this is a function that we're going to use a lot in this class. Okay. Because what a lot of finite elements is we're going to take a differential equation and we're going to set up a system of equations to solve it. Okay. And so the nice thing is that Matlab is really, really good at solving these kinds of systems, right? And so let's say that we have a 3x3 system. So we have 3 equations, 3 unknowns, okay? And so these are our 3 equations, and our 3 unknowns are x1, x2, x3, okay? And so the first step to do is to take this system of equations and put it in matrix form, which looks like this, right? And so we basically just take the coefficients of each of the entries and then pop it into a matrix, okay? And so we have this kind of 3x3 system where this would be like a matrix A, this would be a vector X, and this would be a vector B, okay? And so to solve this in MATLAB, the way that we would have to do this is we had to define the coefficient matrix A, okay? And so that's going to be defined as left-hand side matrix, okay? And we have to define our right-hand side vector B, okay? And so we define it there. I know that I just got done telling you that we don't do this, but this is just an example, just for the sake of simplicity, okay? And so once you've defined your left-hand side matrix and your right-hand side vector, you can use this special operator in MATLAB, the backslash operator, to solve this linear system of equations, right? Because when we have the system here, what we want to solve for are the values of x1, x2, and x3, okay? And we can do that very quickly and very easily in MATLAB by doing x solution is equal to the left-hand side matrix variable backslash the right-hand side vector, right? And so this tells MATLAB that, hey, I have a linear system of equations and I need you to solve it for me, okay? And MATLAB's like, all right, I got you, bro. And then MATLAB will use its algorithms to solve this linear system, and then pop the result into X solution right there, okay? And so this is actually one of the really nice features in MATLAB, is that you can take a linear system and you can literally solve it with 1 line of code. And so this is really nice, and it actually saves us a ton of work in computing things in MATLAB. Okay. All right. So now let's talk about a little bit more advanced programming stuff. So now that we kind of have variables out of the way and we know about solving linear systems, let's talk about conditional statements, or if statements, okay? And so if statements are a very special, function in code, and most programming language have if statements to some degree, okay? And the idea with if statements is that they're a way to build some flexibility into our programs, okay? Because sometimes we want our program to do one thing under a certain set of conditions, and sometimes we want it to do a different thing in a different set of conditions, okay? And the way that we tell our program to kind of account for those different situations is to use an if statement, okay? And so the general format of an if statement looks something like this, right? And so we say if, and then in the parentheses here, we have some kind of check condition, okay? And so that's a condition that we're going to check. And then if that condition is true, then we move into the body of the if statement where we perform, all the work inside here, okay? And so this check condition is what's known as is what's known as a conditional, or in other words, it's what I always learned it as is it's a Boolean statement. Okay. And so a Boolean value is something that can either be true or it can be false. Okay, true or false. Right. And so it's a binary kind of thing, right? And so if this condition is true, then you move into the body and you perform all this work here. Okay. If it's not, then it just skips this line of code entirely. Okay. All right. And so even though in this example here I only have one line of code, you can actually have as many lines of code inside the if statement as you want. It's just I put one here just to be compact. Okay. All right. And so again, if the condition is false, then this entire thing will be skipped, and so the program won't even see the stuff in here. Okay. Right. And so it really depends on if the check condition is true or not. Okay. All right, and so let's look at a couple examples to kind of see this in action, right? And so we can see here I've defined a variable, and so I've defined a variable to have a value of 3. Okay. And so now we go into the if statement, and so if the value of this variable is less than 5, okay, then we're going to go into the if statement, right? And so let's check this conditional, and so we check to see, is 3 less than 5? Okay, is 3 less than 5? Yes, it is less than 5, so this is true. Okay, and so since this is true, we're going to go into the body of this if statement. Okay, and so in the body of this if statement, we can see that we corrected the value of needs correction to 5. Okay, and so at the conclusion of this line of code, the variable needs correction is going to have a value of 3. Okay, now let's look at an example of kind of the opposite situation, right? And so let's say that our variable now has a value of 9. Okay. And so now we go into our check condition, right? And so we check to see, is 9 less than 5, right? Is 9 less than 5? No, it's not. And so this is going to return false. Okay. And so since this is false, then the program is going to ignore everything in the if statement. Okay. And then at the conclusion of this code, needs correction is going to have a value of 9 because we didn't go into the if statement. Okay. All right. Any questions on this? Okay. All right. And so we can do more with if statements. Okay. And so sometimes there's more than one condition that we want to check, right? In case the first one fails, right? And so if the first one fails, then we can check another condition using the keyword else if. Okay. And the way that you do that is like this, right? And so we use the the keyword else if, and we put a second condition, right? And so the way to read this block of code is that the first thing that the program is going to check is condition 1, and so if that's true, then the program is going to execute this line of code here called do this work, okay, and then ignore everything else, right? And so if condition 1 is satisfied, then it just chooses that and it ignores everything else, okay? On the other hand, if condition 1 is false, then we're going to ignore this first part of the code right here, okay? And then it's going to check if the second part of the condition is true, okay? So then it's going to check condition 2, and then if condition 2 is true, then we're going to move on to this block right here and do all of this work right here, okay? But if both condition 1 and condition 2 are false, then we do nothing. Then nothing is done, okay? All right. All right. And so this is kind of another way to kind of add more flexibility into your code. And so I have kind of 3 examples here. And so I think in this first example, what I have here is a case where the first condition fails, right? And so we have a value of 11. We check if 11 is less than 1. That's not true. And so this is going to be false. But then we check if 11 is greater than 7, then that's true. Then we execute this line of code right here. Okay. All right, now we have a situation where the first condition is true, and so we say that needs correction is less than 1, which is true here. Then we're going to execute this line of code, and then ignore everything else. Okay. And in this case, I picked a case where neither is true, right? So needs correction is 3. Since 3 is not less than 1, then we're going to X this out, and then we check to see if 3 is greater than 7. That's also false, and so we're going to ignore that. And so at the end of this, needs correction and have a value of 3. Okay. All right. And so that's a way that you can add else if into your into your programming. Okay. Any questions on this? Okay. All right. And then the final phase of the conditional statement is else, right? And so if all the conditions fail, you can kind of have like a if all else fails kind of case, right? And so if you still want the program to do something if the first 2 conditions fail, and so let's say condition 1 is false, condition 2 is false, then we can enter the else part of this loop or this if statement and do this section of code. Okay. And so the else statement basically ensures that whenever you enter the if statement, something gets done. Okay. And so, I have an example here where, it's kind of an extension of that last example, where if needs correction is less than 1, which is not true, then we check if needs correction is greater than 7, which is also not true. Then we go into the else statement. And so since the first 2 conditions fail, then we're going to execute this one right here. Okay. And so at the conclusion of this line of code, or this block of code, then the variable needs correction is going to have a value of 4. All right. Any questions on this? Okay. We won't do too much in this class with else if and else. Maybe with some else statements. But it's good to know just for kind of general programming, kind of in general. All right. And so now we've gotten to for loops, right? And so for loops are, I would say, a very essential part of this class because we're going to do a lot of repeat work. Okay. And so for loops are basically ways for you to repeat, certain programming statements. Okay, because there's going to be a lot of situations where we want to take this line of code and then repeat it over and over again. Okay, and so the way you do that is with the for loop, right? And so the syntax of a for loop is like this, right? And so you use the keyword for, right? Whenever you type a word in Matlab and then it highlights in green, that means it's a keyword. That means it's a reserved name. Okay. And then from there, you have to define what's called a loop index variable. Okay. And we'll come back to this in a sec. And so that loop index variable is very useful. Okay. Then we define the starting value for the loop and the ending value of the loop, or the last to visit. Okay. And then this loop is going to repeat, however many times it takes to get from start to stop. Okay. And then inside the loop, this is the code that we're going to repeat. Okay. All right, so let's talk about this index variable again, because this is, I think, probably the most useful part of a loop and kind of the reason why we have it to begin with. Okay. And so this index, is kind of a way for the program to keep track of how many times we've executed this loop. Okay. And I don't think I've written that down. Okay, I've kind of written it down, but the index, because the program kind of has to keep track of how many times it's executed the loop, and this index kind of keeps track of that, right? And so the way that you can kind of think of that is that index, the way that it starts is that it starts at the starting value, okay? And then it's going to repeat this line of code, but each time that it repeats, the index is going to count up by 1, okay? And so on the first iteration, index is going to be 1. On the second iteration, index is going to be 2. On the third iteration, the index is going to be 3, and so on and so forth. And then it continues to do this until index reaches the stopping value. Okay. All right. And so how do we use for loops, right? So for loops, I think, is one of the most common programming syntaxes out there, but we actually use it for a very specific for a very specific reason in finite elements. And that reason is to visit every entry in a vector. Okay. Because a lot of times in this class, we're going to create empty vectors or empty matrices, and we're going to want to visit every single entry in that matrix, right? And so we're going to want to visit the first entry, visit the second entry, visit the third entry, the fourth, and the fifth, okay? And kind of the most efficient way to do this is with a for loop, right? And so let's have this very simple example here where I have a zeros vector, which is 1 row and 5 columns across, right? And so let's say that we want to visit every entry in this 5 entry vector, okay? And so to do that, we can write a for loop, and we say for index is equal to 1 to 5. And so this tells us that index is going to count up from 1 to 5. Okay. And we want to repeat this line of code, 5 times. Okay. All right. And so you'll notice here that I've used the loop index as actually part of the code. Okay. And so this is one of the most useful things of using for loops. Right? And so remember, index is going to start at 1, and then it's going to count up to 5 through each iteration of the loop. Right. And so on the first iteration of the loop, index is going to be equal to 1. And so we can say that loop vector at 1. Okay. This is going to be equal to 2 times index, which is 1. Okay. And so this tells us that the first entry of the matrix, or first entry in the vector, okay, the loop vector at 1 is going to be equal to 2 times 1. Okay. And so that's what we see here. And so the first entry here is 2. Okay. On the second iteration of the loop, index is going to be incremented, right? And so from there, index is going to be equal to 2, right? And so now we're assigning the second entry in the vector, right? And then we're going to say that loop vector at 2 is equal to 2 times 2, which is 4. Okay. And then for the third iteration of the loop, index is going to be 3. And so we're going to be visiting the third entry in the matrix. Okay. And so we're going to say the third entry is equal to 2 times the index, which for the third iteration is going to be 3. Okay. And so we have 2 times 3, which is equal to 6. Okay. And then we continue and repeat this until we reach the end of the loop. Okay. So that's one of the most useful applications of the loop in Matlab is to, especially when you have a very large vector, right? So this seems pretty trivial because it's only 5 entries. But again, instead of 5, imagine that we have to visit all 10,000 entries in a vector. Okay, I guess I wrote 100,000. Okay, and so we can very easily change this loop. And so instead of 1 to 5, we can have this be 1 to 100,000. Okay, and so we can do the work of assigning, 100,000 entries in a vector with literally just 4 lines of code like this. Okay. And so that's where the power of loops really comes in, is when you have these, very, very large systems that you have to visit every single entry, and you can do so with the loop, very, very easily. Okay. Okay. Any questions on this? Okay. All right. Oh, and this just kind of walks it through. So I forgot I had this slide. And so this slide here basically kind of explains kind of that example that I had before. Okay. And so, the key here is using that loop index, to update, different entries of the vector as we go along. Okay. Okay. And so in addition to regular for loops, we can also have nested for loops, right? And so this is like the exhibit thing where it's like, hey, we heard you like for loops, so we put for loops in your for loops. Okay. And so you can have for loops inside your for loops to do even more work. Okay. And so when you have a for loop, when you have a nested for loop like this, we have what's called an outer for loop. Okay. And so the outer for loop is the one that's kind of on the outside. And then we have the inner for loop here on the inside. Okay. Pimp my loop. Right. And so, the way to kind of read this is that, the outer for loop is going to execute this many times. Okay. And the inner for loop is going to, execute that many times as well. But each time the outer for loop iterates, then the inner for loop is going to do a full cycle. Right. And so I think the best way to kind of illustrate this is with the hands of a clock, right? And so if you have an analog clock, right, you have an hour hand and a minutes hand, or even you could think of it as like a minutes hand and a and the seconds hand, right? And so anytime, every time the minutes finger goes from one entry to the next, the seconds hand has to make a full rotation, right? And so every time the seconds hand makes a full rotation, then the minutes hand increments by 1. Okay. It's the same thing with nested for loops, right? And so in order for the outer index to increment by 1, then the inner loop has to do a full cycle, right? And so the inner loop is going to do a full cycle. Okay. Then the outer loop increments by 1, and then the inner loop is going to do another full cycle, right? And so this inner loop actually does quite a lot of work because it has to do quite a few cycles, right? Because every time the outer loop increments, then it's going to, do another full cycle just like that. Okay. And so, it's a way to kind of, do a lot more work on repeat. Okay. But kind of the benefit of doing this nested for loop is that now we have two indices that we can work with. Okay. And the best way that we can utilize these two indices is to assign values in a matrix. Okay. And I think I have an example of that on the next page. Right. Because in the example that we had on the previous page, it's just a one-dimensional object, just a one-dimensional vector, right? And so to assign the values in a one-dimensional vector, we only just need one loop index, right? But for a matrix, it's a two-dimensional object, right? So we have rows and columns, right? And so kind of the most natural way to assign values in a system like this is to use a nested for loop, okay? And I believe I have an example of that on the next page. Right? All right, any questions on this? Okay. Right, and so here's the example of that, right? And so, in this example, we have a matrix, right? And so this matrix has 3 rows and 5 columns, right? So it's 3 by 5. And so let's say that we want to assign a value to each entry in that matrix, right? And so one way that you can do this very elegantly with a nested for loop is to have one loop index correspond to the rows and another loop index corresponding to the columns, right? And so we're going to assign this basically assign this matrix, one row at a time, okay? And so let's take the first row, right? And so for the entire first iteration right here, row index is going to be 1, okay? And so we're going to be working on just this row in the matrix right here, okay? And then column index is going to iterate from 1 to 5, right? And so, when column index is 1, then we're going to access the row index, column index entry, right? And so this is going to be the 1, 1 entry. And that's going to be equal to our variable count, right? Okay. Where count is starting at a value of 1, okay? And then we're going to update the value of count. And so the next entry is going to be 2, 3, 4, 5, right? Because we're looping this column index. This column index loop has to make a full cycle before we return back to the outer loop, right? And so now that we've returned back to the outer loop, we're now on the second row, okay? And then now we start counting like this, okay? Oops, 8, 9, 10, okay? And so that's how we can kind of elegantly visit every entry in a matrix like that, okay? All right. And so one thing you'll notice here is that when you have a nested for loop like this, sometimes it's useful to have what's called a counter variable, right? And so the counter variable is a variable that kind of exists outside the loop and kind of updates its value kind of semi-independently, okay? And I think it's a little bit hard to explain the use of counter variables without kind of a more example. And so I'll kind of leave it there. And I think we have some examples after this, okay? But the use for the counter variable here is to make sure that we're always kind of counting up as we assign the values in this matrix, okay? All right, any questions on this? Okay. All right, and so here's what the resulting matrix looks like at the end, right? And so, again, we built this matrix kind of row by row. So since the row index was from the outer loop, we built the matrix going this way first, then we went to the second row, and then we built the matrix going this way, and then finally we built the matrix from that row just like that. Okay. Okay. And then finally, I think the last thing, I think this is the last piece of content that we have is we can put if statements inside for loops as well, right? And so this is kind of one of the more common uses of if statements, is that we can basically tell Matlab, or we can tell any program, to do a different set of instructions or to do a different task depending on which iteration that we're on. Okay. And so in this example right here, where we only want Matlab to do something for the even entries on this vector right here, right? And so you can see here that we've created a vector here with that's 20 by 1, okay? And then we're going to use this if statement right here to check and see if we have an even number, right? Right. And so the way that you can check it for an even number is you can use this special MATLAB function called mod, okay, which basically takes a division between these two variables. Okay, let me clear this up. Okay, and so we're going to take a division between the vector index and 2, and then if that remainder is 0, then we know that we have an even number. Okay, and so if we have an even number, then we can assign a value here. And so you can see the result here, where all the odd number entries are still 0. Whereas the even number entries have values to them because our if statement here was satisfied. Okay, and so you can have if statements inside your for loops too, and this is useful for when you want to do something different depending on the entry that you're in. Okay, or depending on the index that you're on. Okay, and we'll make use of this too because oftentimes in finite elements, you're building your matrices, you're building your vectors. You often want to do something different at the extremities of the matrix, okay, and that has to do with boundary conditions, right? And so if statements are a great way to do this because you can kind of incorporate that directly into your code, and you can tell MATLAB to do something different at the boundaries, compared to the middles of the for loop. Okay. All right. Any questions on this? Okay. All right, so now let's do an example. I think I have a couple examples here. I think we have just enough time to do them. Okay. All right, and so in this example, we're going to start with an empty 5x5 matrix. Okay, and so we can write the code to do that. Okay, and then we want to fill each row of the matrix according to the following criteria. Right, and so the first row of the matrix we want to start with 2. Okay, and then we want to count up by 2 in each subsequent entry. Right, and so that means our second entry is going to be 4. Our third entry is going to be 6. Our fourth entry is going to be 8. And our last one's going to be 10. Okay. And the second row, we're going to start at 3, and then we're going to count up by 3 on each entry. Okay. Okay, so it's going to be like that. And the third row is going to start at 4, and then we're going to count up by 4. Okay. Right. 20. Okay. Dot, dot, dot. Right, and so we're going to write the MATLAB code to do this. Okay, so I think normally, when I had this originally planned, this was going to be an interactive activity where I have you work on it. But since we are running a little bit short on time, I'm just going to show you the solution for this. Okay. All right, and so this is basically a problem for how we do a nested for loop, right? And so the first line of code here, we can see that we use the zeros function. Okay. And so you can see that we've used the zeros function to create an empty 5x5 matrix. Okay, and then we're going to create, and then we're going to assign values of this matrix, using this nested for loop. Okay. All right. And so the code here is as follows. And so we have an outer loop here that loops over the rows, right? And so kind of just like loop 4. Okay. And then inside this loop, we have a variable here called count. That's going to have a value of row index plus 1. Okay, and so the first iteration of this loop, our row index is going to start at 1, and so this count is going to be 1 plus 1, which is equal to 2. Okay, and so before we jump into the inner loop, the count here is going to have a value of 2. Okay, and then we're going to jump into the inner loop here, right? And so for the inner loop, we're going to loop across the columns, and we're going to go from 1 to 5, right? And then we're going to assign the values according to this value of count right here, okay? And so for the first iteration, this row index is 1, and then this column index is also 1, and so the 1, 1 entry, okay? And then, which is this guy right here, okay? We're gonna assign that value of count, right? And then what we're gonna say is that before we move on to the next iteration of the inner loop, we're gonna update the value of count, right? And so what we're going to say is count is equal to count plus row index, where row index here is 1, plus 1. Okay. And so what we're going to say is that count is equal to 2 plus 1 plus 1, which is equal to 4. Okay. And then after this, we're going to go on to the next iteration of this inner loop. Right. And so now column index is going to be 2, but row index is still going to be 1 because we haven't yet returned to the outer loop yet. Okay. And so now that the column index is 2, we're gonna modify the 1, 2 entry, okay? And so now that's going to be the new value of count here, which is 4, okay? And so that's going to assign this this value right here. Okay. And then again, we're going to update the value of count, right? And so, right. And so if we update the value of count, right? And so the value of count from before was 4, right? And so we do 4 plus row index. Row index here is still equal to 1 because we haven't returned back to the outer loop yet. Okay, plus 1. And so the result of this is going to be 6. Okay, and you can see that we have assigned a value of 6 here, you know, and so on and so forth. Okay. And so for these examples, I would actually highly encourage you to try to kind of, just go based on the problem statement. Okay. Go based on the problem statement and see if you can write this code on your own. But if you need some help, you can look at the solution, but really kind of take it apart, kind of line by line, and see if it kind of makes sense in your head. Go through the loop iterations kind of one by one, and kind of mentally kind of do it yourself. To say, like, okay, the first iteration of the loop, we start at 2 here, and then we update the value of count, so now it's 4. We update again, we're 6. Okay. And then after this loop completes, then we return back to the outer loop, and then the value of count is reset. Okay. And it's going to reset to 3. And so that gives us this, and so on and so forth. Right. And so kind of do the same kind of exercise that I'm kind of doing with you guys right now. Really talk your way through these loops and really try to make sense of it, and to see if it kind of makes sense that, that this chunk of code right here produces this result. Okay. And I think that's a great way to kind of read code like this and to really kind of help you kind of master this stuff, right? And so, ultimately, the best way to learn code is to practice it yourself, right? And so that's why I suggest that you guys, try to do these examples on your own. But when you're trying to read code like this, try to logic it out. Try to see, when I give you code like this, try to read through it and make sure that everything in the code kind of makes sense and it follows that same logic that produces this this result here. Okay. Okay, any questions on this example here? Okay. All right, and so here is here's the second example. Okay, so for the second example, we're starting with an empty vector that's 25 entries. Okay, and then we want to loop over each entry and modify the value according to the criteria. Right? If the index is an odd number, then we're going to change the entry to 1. If the index is a multiple of 4, then we're going to change the value of the entry to 4. But in all other cases, then we're going to assign a value of 24. Okay. And so you can see here that, because we have different use cases, right? It's even in these statements right here. You can tell that we're going to be using if statements in this example, right? Because we're going to do something different depending on what the index of the loop is going to be. Okay. And if you look at the example right here, then this kind of shows you kind of exactly that, right? And so first we check to see if we have an odd number. Okay. And so if we have an odd number, then the modulus of the index and 2 is going to be equal to 1, right? And remember, the modulus is a remainder operator. And so if we do that, then we assign a value of 1. Else if we're going to check to see if it's a multiple of 4. And so if it's a multiple of 4, then modulus vector modulus 4 is going to be equal to 0. Okay, then we can assign a value of 4 there. But in all other cases, we're going to assign a value of 24. Right? And so the result of that code is given to you here on this vector as well. Right? And so once again, kind of walk your way through this, right? And so kind of walk your way through the loop. And so you can say, in the first iteration of this loop, vector index is going to be equal to 1. Okay, and so if we say we take the modulus of 1 divided by 2, and we see that the remainder of that is 1, and so we're going to enter this entry of the if statement right here, and then ignore everything else. Okay, and we can see that we assign the value of 1 here, just like that. Okay, and then do that for kind of every iteration of the loop, until you kind of build up this vector just like that. Okay, any questions on this? Okay. All right, and so the last thing I want to talk about today is plotting. And so one of the nice features of Matlab is that it allows you to plot data and visualize it very easily. Okay, and so the way you do that is with a plot function. Okay, and so the first thing you're going to do is you're going to create a figure and you're going to plot. Okay, and then you need to put 2 entries here, one for the x-axis, one for the y-axis, and then that creates a plot for you, like I'm going to show you on the next page. Okay, right, and so here's an example of how you're going to plot stuff. Okay? And so we'll use plotting a bit in this class just because it's a nice way to kind of visualize the data. And this is kind of basically how you do that. And you can add a title, and you can add labels to your x and y axes as well. Okay. All right. Any questions on this before we wrap it up for the week? Okay. All right. And so that's a crash course in MATLAB in a nutshell. So I know it was a lot of information today, and it's kind of really hard to imagine doing this stuff, but I wanted to have this kind of tutorial kind of at the beginning, so that when we start to do MATLAB together in the class, when we start writing finite element code, we can refer back to this MATLAB tutorial and say, this is, we're updating the variable, and this is what we're going to do, right? And so I know it was a lot of information, but I put it in this form, in the form of a PowerPoint slides on purpose, so that you can kind of keep referring back to this, as we go through the semester, right? And so, I definitely don't expect you to kind of retain everything that we talked about today, because it was a lot of stuff, but just remember that we talked about this stuff, and then use these lecture slides to refer back to as we write more code for the class. Okay. All right. And so on Monday, actually, we're actually going to be doing an ANSYS activity. Okay. And so the first of 2 ANSYS activities that we're going to do in this class. And the reason I have that ANSYS activity early is because, after doing all this MATLAB programming, I kind of want to, remind you of kind of what our end goal here is in this class, is to write finite element code. And I think one thing that ANSYS does really well is that it kind of really illustrates that whole process of going from, geometry to finite element solution. Okay. And so we're going to be doing a very simple ANSYS activity on Monday. Okay. All right. So thank you guys for tuning in today. I know I went a little bit over time, so I apologize for that. And so I hope you guys enjoy the rest of your evening. I hope you guys enjoyed your weekend, and I will see you on Monday.
Thanks, Professor. Have a good one.
Thanks, guys. Question. So, so does the plot line need a semicolon? Yeah, it's a good question. And so the semicolon, what it does, in reality, you're right. I should have had a semicolon here, but because this title function doesn't produce any output, then you can leave the semicolon off, and it's not going to produce any error. Yeah. Yeah. Mm-hmm. Yeah, but most of the cases you want to put a semicolon after everything. Mm-hmm.
Professor, could you
Yep.
explain how the mod function works here?
Yeah. So the mod function is basically a remainder function, and so I think when everyone kind of first learns division, they only remember in whole numbers, right? And so if you take 9 divided by 2, right? And so if I ask like a graduate student in engineering, they'll tell me it's 4.5, right? Because
Yeah.
we know decimals. But for if we just stick to just integer values, what we can say is that this 9 divided by 2 is 4, remainder 1, right? Right? And so this mod function basically gives you what this remainder is. And so it performs a division between these 2 entries, and it doesn't give you the result here. It gives you what the remainder is. And so it's a great way to test, if you have an even number, an odd number, or if you have a multiple of a certain number. Yeah.
Okay. Thank you.
Mm-hmm. Right. Ryan, do you have any more questions? Okay. All right, if there's no more questions, I'm gonna go ahead and sign off. So enjoy the rest of your evening, and I'll see you next week.
Goodbye, Professor. Take care.
Yep, you too. Take care.